Hello. In this video, we're going to look at some applications of integration. Now, primarily, we're going to look at some applications from physics. So hopefully you've taken at least grade 10 or grade 11 physics, but if you haven't, I'm going to do my best to explain, and you can hopefully follow along with the intuitions here. So let's say we have a ball that's tossed up in the air with an initial velocity of 20 meters per second. In this case, we're going to imagine the ball is just tossed straight up and then it's going to come back down. Now we want to create a function that gives the position of the ball at any point in time. And finally, we want to graph this function. Now we're going to assume that gravity is 10 meters per second squared. That's the acceleration of gravity. And we're going to assume no air resistance. Well, a rough sketch here of what's happening would be the ball goes up and then the ball comes back down. But that doesn't really look like a graph. And so what we're going to do is instead, we're going to graph this as the y-axis and this is the t-axis. So over time, what that means is the ball, it goes up and then comes down. So it's not as though you're throwing it between two people, but what's happening is the height is increasing and then the height is decreasing over time. So that's roughly what our picture would look like, and we need to figure out a way to actually model this. This is a function, this is going to be some type of equation. How would we create math to do that? And maybe you remember some stuff from physics, and if you do, you might remember some formulas. So for example, you might remember the following. You might remember that your distance is going to be v naught t plus 1/2 at squared. You might remember that's a formula. Now in this case, we're going to be using y for our distance because we're looking at vertical distance. So y is equal to v naught t plus 1/2 at squared. We know what the v naught is because that's our initial velocity, which is going to be 20. And since it's up, it's a positive 20. And we know our acceleration is negative 10 because it's, of course, accelerating downward. So if we keep cleaning this up, we'll get 20t minus 5t squared. Well, we're firmly in the realm of mathematics now. We know how to do some work here. We could factor out the 5t, and we'll get 4 minus t. So what that means, of course, is that t equals 0 and t equals 4 if you set this thing equal to 0. And so that tells us that we have an intercept here at 0, and we have an intercept over here at 4. So we know that if we were going to actually graph this, so this is going to be our nice graph, not just a rough sketch. We know that we've got an intercept here at 0, we've got an intercept here at 4. Now, what we should know about parabolas is that if we have an intercept at 0 and 4, it means halfway between at 2, that's going to be our maximum because of symmetry. And so we could plug in t equals to 2. And so, well, let's go ahead and plug that in. We would have y equals 20 times 2 minus 5 times 2 squared. So 40 minus, well, 5 squared is going to, or 2 squared, sorry, will be 4. 4 times 5 will be 20. So 40 minus 20, just giving us 20. So over here, we know we're going to have a maximum at 20. And so there's our parabola. We know, of course, right away here, because we have t squared and t, this is a parabola shape, and so it goes something like that, and we're able to label it. But what if we were able to do this with calculus? Would there be some way to do this question without assuming this formula here? Because this is really the issue. Right here, how do you know this? Where did this come from? Are you sure that this is true? Did your physics teacher prove it to you? Maybe you never even took physics. And so from this formula, yeah, the rest of this mathematics follows pretty clearly, but this formula is a bit of a mystery. And so it would be nice if we could find a way to actually do this question without this formula, or if we could find a way to look at this more from first principles, more using just mathematics, not jumping to a formula right away. So let's actually look at the graphs of these on Desmos. In particular, we're going to look at the graph of the position, but then we're going to look at the graph of velocity and acceleration. So here we have the graph of 20t minus 5t squared. This is the shape that we get. This is the up and down motion over time. But what if we were to take the derivative of this, just for fun? Well, the derivative of this would be 20 minus 10t, which would look like this. 20 minus 10t means we're going to have a y-intercept up here at 20, and then it's going to be a slope of negative 10. Well, what this actually represents physically is the velocity of our ball. Now, let's see if that makes sense. As we throw the object upwards, it initially has a positive velocity of course, 20. And then it slows down. It's still going upwards, but the speed is decreasing. When the ball is at the very top of its arc, it has a velocity of 0. And that makes sense because it's not moving at the top. It almost hovers at the top for an instant. And then it has a negative velocity because now it's moving downwards. So this blue graph, the derivative, is actually the velocity, and we got it by taking the derivative of position. Well, what about the second derivative? Well, the derivative was 20 minus 10t, so the derivative of that, if we do it in our head, will just be minus 10. So this is the second derivative, and if you notice, it's always negative 10. Well, we were told that the acceleration of gravity was negative 10. So what we actually have here is the derivative of the derivative, the second derivative, is representing acceleration. So let's try to relate these quantities a little bit. So we had these three graphs. We had a parabola. We had this line here, and then we had another line that was now horizontal. So I should maybe do that last one in red just so we can see. This is the line we're talking about right there. And so this here was just the function. This was the derivative, and this was the second derivative. And it seems that this was position, the position graph. This was the velocity graph. And this was the acceleration graph. Well, how can we now think about this in terms of calculus? Let's take a look here. We have position, velocity, and acceleration, three fundamental quantities in physics and motion. And what it appears is that if we go this way and look at either, you could say the slope, or you could say the derivative, we go from position to velocity. And if we do the derivative again, we get ourselves acceleration. Well, how do you go backwards then? If you have acceleration, all you need to do is the antiderivative to get back to velocity. The antiderivative is also called the integral. And to get from velocity back to position, we also use the integral. So if we go derivative one way, we go backwards using the integral. So let's now try this question again, but with calculus. So what we're told in the question is that the velocity is 20 meters per second initially, and that the acceleration is 10 meters per second, well, downward. So we actually don't know the position and we don't know the velocity. The only thing we know is that the acceleration, or you can think about it a function a of t, is negative 10. That's all we know. But we could use that to find velocity, because if we know acceleration, the velocity is simply equal to the integral of acceleration. Well, what's the integral of negative 10? It'll just be negative 10t plus c. We got a bit of a problem here. We need to solve for c. We need to solve for c. It's no good getting a final equation that's got tons of extra random variables. But I think we can solve for c, because we're told that the initial velocity is 20, which means v of 0 must be equal to 20. Well, let's see what happens when we get v of 0. V of 0 would equal negative 10 times 0 plus c, which would equal c. So therefore, c equals 20. And we have our better formula. V of t is negative 10t plus 20. No variable required. Now let's go ahead and find ourselves, well, position. Position is going to be equal to the integral of velocity. Well, to do that, the integral of negative 10t will be negative 10t squared over 2 plus 20t plus, well, we need another variable, so we'll use the letter d. And now again, we have the same issue. We need to solve for d. Well, let's simplify this a little bit here. So this will be negative 5t squared plus 20t plus d. And let's go ahead and solve for d. We know that the ball is tossed up in the air. Well, what that's telling us is that it's initially y of 0 is equal to 0. It's not going to be off a ledge or anything. It's starting at the very bottom, and then it's going to be tossed up. Maybe we're making a bit of an assumption here, but we're imagining the person is tossing the ball right from the ground. Maybe they have a little bit of height, but we're assuming they're tossing it up from the ground. So initially, there is no height. There's no y value, so y of 0 is equal to 0. Well, that would tell us then that if y of 0 is equal to 0, well, what is y of 0? It'll be negative 5 times 0 squared plus 20 times 0 plus d. Okay, so then we get 0 plus 0 plus d. So therefore, d equals 0. And we have our formula. Y of t is equal to negative 5t squared plus 20t. And if you look back, that's exactly the same formula that we had before. This formula right here is the same formula that comes about using the distance equals to v naught t plus 1/2 at squared, the classic physics formula. But we didn't have to do any physics. All we had to do was calculus. And this question here, you could do this question without knowing any physics background. In fact, this is how the physics is properly done, because there's no need to appeal to some magical formula. We just do calculus. Now let's try another one. A ball is launched on top of a homemade rocket 5 meters tall, with an initial velocity of 0 meters per second and a changing acceleration. This is because the rocket accelerates faster as it loses mass. The function for acceleration, gravity is already accounted for, is measured to be a equals 4 plus 2t. The rocket starts from rest. Calculate a function that gives the position of the ball at any point in time. So the problem with this question is you can't actually use your formulas from physics because we have a changing acceleration. And hopefully this was mentioned in your physics class. All the kinematic formulas that you came up with, they only work when you have a constant acceleration. And so changing acceleration means we can't use our physics formulas. But we actually can use the calculus just like normal. We have our formula for acceleration. And to find velocity, we simply do the integral. So v of t will be equal to the integral of 4 plus 2t dt, which gives you 4t plus 2t squared over 2 plus c. We'll rewrite that nicely as t squared plus 4t plus c. Now we know, of course, that v of 0 is 0 because it has an initial velocity of 0. Now v of 0 is actually equal to, well, 0 squared plus 4 times 0 plus c, which is just c. And so therefore, c is equal to 0. Now, sometimes the constants are 0, sometimes they're not, but we always have to solve for them just to find out what they are. So we have t squared plus 4t as our velocity. All right, well, let's keep on chugging. Let's find y of t, which is just the integral of velocity. So the integral of t squared plus 4t dt, which will give us t cubed over 3 plus 4t squared over 2 plus d. Well, now we need another piece of information, and if you notice here, they tell us that the rocket is 5 meters tall. Well, the ball is sitting on top of the rocket. So y of 0, the initial height of the ball, is 5. So let's use that over here. So y of 0 is equal to 5. Now y of 0 would be 0 cubed over 3 plus 4 times 0 squared over 2 plus d, which will just give us d. So therefore, d is equal to 5. And we have our wonderful formula. So therefore, we would have y of t is equal to t cubed over 3. We could simplify that as just 2t squared plus 5. Now, it's important to note this is not actually a parabola. Because of that cube, this is going to be a cubic function. And let's take a look at what this would look like on Desmos. So here we have the function, and initially it looks a little bit like a parabola. It takes off slow, and you can imagine that rocket here at the beginning just climbing a little bit, but then as we move over, well, the rocket begins to really pick up speed. And because it's accelerating at a changing rate, as you go over, and maybe I can zoom out here a little bit for you, you can see that the rocket, it really begins to get a lot bigger. As you go, the height of this rocket really takes off, and so by the time we're at even just 5 seconds, the rocket is now rocketing up to 100 meters almost. And this rocket is just growing faster and faster and faster, the height of it. So it's quite interesting to see this graph, and it's not a parabola, of course, it's a cubic, and we can come up with that because we used calculus. Let's go ahead and try another example. A particle is moving in a strange electric field according to the following position function. So we have t cubed plus 2t squared minus 6t plus 9. Determine when the function had a velocity of 1 meter per second. Initially determine when the function had an acceleration of 22 meters per second squared. So in this case, they've actually given us the position function, and we need to somehow work backwards and find what the acceleration or find what the velocity would be. Well, that's in some ways, again, just an application of calculus. The velocity function is just the derivative, in this case d dt, of the position function. So since we know the position, we just take the derivative. This gives us 3t squared plus 4t minus 6, and of course the derivative of a constant is 0. Now we want to find when the velocity is 1. So let's set this thing equal to 1 and solve. Well, we move everything to one side and make it equal to 0. That's our usual method. Now we need to find two numbers that multiply to give and add to give. Well, there's a 3 there, so it's a little bit tricky, but I'll help you out with the factoring here. One of the things you can always do with factoring is if you have a prime number as that leading coefficient, you know it's going to be 3t times t to get 3t squared. And then you can just play around with the numbers and you should find minus 1 and 7. If you do group factoring, you'll get the same thing. So you can or use group factoring. Group factoring. So either way, you get this. And so that will give you t equal to negative 7 over 3 and t equal to 1. Well, we know that t had to be greater than or equal to 0, so this one over here we're going to reject. But this is what we accept. And so when is the velocity 1 meter per second? When t equals 1 second. There's our answer. Now we need to find when the acceleration is 22. Well, acceleration is the derivative of velocity. So let's just take another derivative. A of t is equal to the derivative of 3t squared plus 4t minus 6. That'll give us 6t plus 4. And we want that equal to 22. So 22 equals 6t plus 4. So that'll give us 18 is equal to 6t, and t is equal to 3 seconds. So there we go. We've been able to find where the velocity is the required value and where the acceleration is the required value. Again, just using simple applications of calculus. So a few more examples here. If the position of a particle is given by this formula, find the time when the particle changes direction. Well, changes direction. When does something change direction? Well, if we think about that ball example, when it was thrown up and it went from going up to going down, if something is changing direction, the velocity has to be equal to 0 because it initially is going forward and then going backwards. When it pivots from one direction to the other, at that moment, the velocity is 0. So let's see if we can find when the velocity is equal to 0. Velocity will be the derivative of position. So we've got ourselves a nice derivative question to do. So we get 3t squared minus 24t plus 36. Looks like we can factor out a 3. So we get 3 times t squared minus 8t plus 12. We'll set this equal to 0. And we'll get, looks like t minus 6. And t minus 2 should work. So that gives me t equal to 2 or t equal to 6 here, sorry, and t equal to 2. Well, those are both in seconds, likely. It doesn't actually say on the question, so maybe we can leave them without units. T is equal to 6 and t is equal to 2. And those are the times when the particle changes direction, because that's when the velocity is 0. Let's do another one here. A car is traveling at 30 meters per second when the driver sees an accident 80 meters ahead and slams on the brakes. What constant deceleration is required to stop the car in time to avoid a pileup? All right, well, this is actually a very important problem. We want to find out what we have to do to not end up in an accident. So let's see what we could do. Well, we need to figure out the deceleration, and we know it's constant. So in other words, a of t is just equal to k. It's a constant acceleration or deceleration. Well, there's not really much to do here other than integrate, so let's go ahead and find velocity, might as well. It'll be the integral of k dt. Integral of a constant will be the constant times t, and then we have to add another constant. Ooh, there's a lot of letters getting involved here, but we know that the car is initially traveling at 30 meters per second. Well, that tells us that v naught, or v, sorry, not v naught, v of 0, you could think of it as v naught, is going to be 30. So v of 0 is equal to k times 0 plus c, which will just be c. So then that will give us c is equal to 30. So our formula for v of t is kt plus 30. We were able to find the c, but we still haven't found that k value. Well, let's try to integrate again. So I'll use s for position. Sometimes you use x or y or s. Those are good letters to use for position. So s of t will be equal to the integral of kt plus 30 dt. And that'll give us, well, kt squared over 2 plus 30t plus, well, we've got another constant, d. Well, we need to solve for that one. And do we know anything about position? Well, it doesn't really tell us, but we have this 80 meters. Let's assume that the position is initially 0. We can assume the car is starting wherever we want, and then eventually we're going to use this 80 in some other part. So let's say you could say the position initially was negative 80, but let's say where we're starting this formula is where the function starts. So we'll say s of 0 is equal to 0. Well, s of 0 would be equal to k times 0 squared over 2 plus 30 times 0 plus d, which will just be d. So then, therefore, d is equal to 0, and we'll get s of t is equal to kt squared over 2 plus 30t. And the thing is that we want something from this. We want this to not pile up. And so something has to happen here so that we avoid the pileup. We don't want the car to hit, of course, the accident ahead of us. And so we need to do something. Now, in particular, we're going to want the velocity to be 0. So we want v of t to be equal to 0 because we want to be stopped. That's what it means to be stopped. It means we have no velocity. Well, when would v of t be equal to 0? We could solve that. kt plus 30 equals 0. So we'd have, I guess, kt equals negative 30. And let's say we were trying to solve for the time that happens. Time would be equal to negative 30 over k. We don't know k, unfortunately, and so this doesn't tell us when it's going to be stopped, but it gives us a value for t. Because this here, we have an equation with t and k, and oh, hey, look, we have an equation over here with k and t. Could we take this value for time when it's supposed to be stopped and plug it in to the position? Well, maybe. Let's see what we would get. So on the one hand, we'd have some kind of s of t business. And on the other hand, we'd have k times negative 30 over k squared over 2 plus 30 times negative 30 over k. But this still isn't going to allow us to necessarily solve for k because the left-hand side over here is just s of t. And so the other thing we know is that when it's stopped, we also know that it happens 80 meters later. So we can make that left-hand side, the position will be 80 meters. So 80 meters is when it's stopped. That's the position. And we have k, well, this will be 900 over k squared. I'll put the 2 over here. This will be, oh, we should make that negative 900 over k. So let's start to clean this up a bit. 80 equals, well, 900 over 2, we could simplify that to 450. And k over k squared will just give me a k on the bottom. Oh, this is looking pretty promising. We could common denominator those and just get 450 negative over k. We could cross multiply the k and the 80, flip those around, to give us that k is equal to negative 450 over 80, or k is equal to negative 45 over 8. Well, there we have it. That's what we were looking for. We need to decelerate at 45 over 8 meters per second squared. And if we decelerate at that rate, we should avoid the crash. Now, one more question here. Let's give ourselves a crazy acceleration formula and try to find position. Well, v of t will be equal to the integral of 3t squared plus 2t plus 1. That'll give us 3t squared, 3t cubed over 3, plus 2t squared over 2, plus t plus c, which cleans up as just t cubed plus t squared plus t plus c. Now, unfortunately, we don't know anything about v, so we have to integrate again. So that gives us position is equal to the integral of t cubed plus t squared plus t plus c, or t to the 4 over 4 plus t to the 3 over 3 plus t to the 2 over 2. Well, the integral of c will be c times t, because the derivative of c times t is back to the c. Then we need another variable d. So we have two variables, but we have two pieces of information. S of 1 is 2 and S of negative 1 is 1. So let's plug those in. Let's find out what we get for S of 1. S of 1 gives us 1 over 4 plus 1 over 3 plus 1 over 2 plus c plus d. We should probably clean that up a little bit. So using your fraction knowledge, we could make all of these over 12. So this would be 3 over 12 plus 4 over 12 plus 6 over 12 plus c plus d, which will give us 13 over 12 plus c plus d. And so therefore, Since s of 1 is 2, we could say 2 is equal to 13 over 12 plus c plus d. Oh, well, we can keep going here. This would give us, if we move that to the other side, 2 minus 13 over 12 equals c plus d. Or, well, that'll be 24, so 11 over 12 is equal to c plus d. Unfortunately, though, this equation has two variables. So let's try again. Let's try the other value, see if maybe that works a little better. S of negative 1. S of negative 1 will be 1 over 4, because the negative 1 squares away, minus 1 over 3 plus 1 over 2, minus c plus d. Again, if we use our fraction knowledge here, this will be 3 over 12 minus 4 over 12 plus 6 over 12 minus c plus d. And that will work out to give us 5 over 12 minus c plus d. Well, since s of negative 1 we know is 1, 1 is equal to 5 over 12 minus c plus d. If we move that to the other side, we have 1 minus 5 over 12 equals negative c plus d. And so that would give us 7 over 12 equals negative c plus d. So here we have an equation with c and d, and here we have an equation with c and d. Well, we have two equations and two unknowns, so we can solve that. And these ones look nice. We can do elimination by just adding these two equations together. So we're going to do the elimination method here. And so we'll get 11 over 12 plus 7 over 12 equals c plus d minus c plus d. That gives 18 over 12 equals 2d. Well, we could simplify that a little bit over here. 18 over 12 we could divide by 6 and divide by 6, so that'll be 3 over 2 equals 2d. And so d equals to 3 over 4. Well, we could then sub that in. So now we'll go back and find c. So negative, or I guess we'll use the first one, 11 over 12 is equal to c plus 3 over 4. So c is equal to 11 over 12 minus 3 over 4. That'll be 11 over 12 minus, we'll have to multiply by 3, so 9 over 12. So we'll get 2 over 12, which is going to give us 1/6. And so putting that all together, s of t is equal to t to the 4 over 4 plus t to the 3 over 3 plus t to the 2 over 2 plus, well, c was next to the t, so 1/6 t, and then d was just on its own, 3 over 4. And there we have our formula for the position. So make sure you try some of these exercises. Again, the answers are in the back, as well as the full solutions are on the website. And as always, thanks for watching.